Yes, lads, we've got another step question, and this is the second one I'm doing from the 1993 paper, step 2. The integers a, b, and c satisfy 2a squared plus b squared equals 5c squared. By considering the possible values of a mod 5 and b mod 5, show that a and b must both be divisible by 5. So that's sort of a part A to the question. And then the next part B, by considering how many times A, B, and C can be divided by 5, show that the only solution is A equals B equals C equals 0. Alright, so the first part, by considering the possible values of A. When we think possible values and we see mod 5, we immediately think to consider the residue classes of A and B mod 5. So let's start with A first. Then deal with a squared, then 2a squared. So let's draw a table to represent this. So we've got our possible values, and let's write this as residue classes. So since we're working mod 5, we'll go from 5k plus 1, plus 2, plus 3, plus 4, stop being lazy, I'll write in. And 5k plus 5 is congruent to 5k mod 5, so we don't need to consider that. And then, what do we need to write? Well, a squared. So yes, just need to point out that these are all potential values for a. So a squared, 2a squared, and then we can write 2a squared mod 5, because that's what we're working in. So 5k, should we apply the mod earlier, because the question states of a mod 5, but we'll see. So a squared, 25k squared, 5k plus 1 squared, 5k squared plus 10k plus 1, a squared again, 25k squared plus 20k plus 4, 5k plus 3 squared, 25k squared plus 30k plus 9, and then 5k plus 4 squared is 25k squared plus 40k plus 4. So this is sort of like long. Now we've got some nasty looking quadratic expressions. So we're actually going to go ahead and do what the question did and work with mod A from the get-go. So let's get rid of all this and write mod 5a. So that's just 0, 1, 2, 3, 4. Then mod 5, should I just consider a squared, mod 5, a squared, 0, 1, 2 squared is just 4, so that's congruent to minus 1. 3 squared is 9, mod 5 is 4, which is also minus 1. 4 squared is 16, which is just congruent to 1. Now 2a squared, mod 5, 2a squared, so we just get 0, 2, minus 2, minus 2, and 1. Oops, that should be a 2. Right, we've considered A. Can't really do much with this as of yet. But let's go on to B. So let's copy this table out. And we're just working with b squared now. not 2b squared, that's right. So we've got 0, 1, 4, which is same as -1. 3 squared is 9, so that's also -1. 4 squared is 1. Now, how does this actually help with the question? So by considering the possible values of a mod 5 and b mod 5, show that a and b must both be divisible by 5. Right, so a and b are both divisible by 5 when they equal 5k. We should actually be using different letters. Let's use n, 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 and n. Now, if you look at the residue classes of b squared and 2a squared, they both have 1s, -1s, -1s, and 1s, 2, -2, -2, and 2. Now, obviously, we're doing 2a squared plus b squared. So if we add these, there's no combination such that a residue class from a squared and residue class from b squared add up to give us 5. And why we need 5 is because, well, on the right hand side we've got 5c squared. So the only value that actually gives us a multiple of 5 is this one, 0 plus 0. Because if something's 0 mod 5, it means it must be divisible by 5. And yeah, none of these other values such as 1 add 2, 3, 1 add -2, -3, -1 add -2, -3. None of them give us either 0 or 5 or anything congruent to 0 mod 5, so we ignore them. So from all that, yeah, we can deduce that A can be written as 5k, B can be written as 5n, and that shows that A and B must be only multiples of 5. So that's the first part done. And let's keep a note of that because that'll probably be helpful in the next part. Now, by considering how many times A, B, and C can be divided by 5, show that the only solution is A equals B equals C equals 0. Alright, so let's write our equation again. 2a squared plus b squared equals 5c squared. Now, we know A is divisible by 5, B is divisible by 5. What about C? Well, we can sort of guess that C is going to be divisible by 5 just by looking at the pattern, but let's just prove it. So let's substitute in 5k and 5n. 5k squared plus 5n squared equals 5c squared. Divide through by 5 on each side, so we have 10k squared plus 5n squared equals c squared. Factorize out of 5, so we have 5 times 2k squared plus n squared equals c squared. C squared, 5 divides c squared. That means, and since 5 is a prime factor of c squared, we can safely say that 5 also divides c, which is perfect. So if we go back to our equation now, plus b squared equals 5c squared, each of our terms a, b, and c are divisible by 5. So let's go ahead and substitute a equals 5k, b equals 5n, and let's say c equals 5j, where k, n, and j are integers. Don't know whether they're positive or negative. Let's just say they're integers. I mean, we should also write that a, b, c are not equal to 0, because if they were, then this would be 0 plus 0 equals 0. And that obviously satisfies the equation. So, yeah, let's see. Does there exist a case where a, b, c are not equal to 0 and we get a solution? If there is, we're in a bit of trouble. If there's not, we can say that a equals b equals c equals 0. So let's sub in our values. 2 times 5k squared plus 5n squared plus 5j squared Now each of these terms have 25 in them, so we can just divide by 25. So we have 2k squared plus n squared equals, this should be written a bit better, 5 times 5j squared. So that equals 5j squared. And look, we've got the same format as what we did here. So we can sort of deduce that k and j, which are also integers, must also be divisible by 5. And if you do the same again, let k equal some, let's say, some integer, q, n equal 5, r, and j equals 5s. We're going to put these numbers back into this equation, and we're going to get the same structure again. So we've got sort of this infinite cycle of equation type. Now how does that help us? So originally we started by saying that a equals 5k, and k was also a multiple of 5, so we said k equals 5, what do we say, 5q. And we could also say that q is divisible by 5, so we say 5 times 5, I don't know, let's say d, and so on and so forth. So that means a has an infinite number of factors of 5. So what can the value of a actually be? Now using infinite descent, we can deduce that a can only equal 0, because 5 can divide, well, we can have an infinite number of 5s dividing 0, 5, let's say 5 to the n, and we'll still get 0. However, if we have, for example, 125, so this is the case where a equals 0, when a does not equal to 0, we know that there are only finite numbers between a and, let's say, a and 0, finite numbers. Well, we just said that there was an infinite number of factors of 5 for a. Well, this can't be true. That's obviously a contradiction to this statement. This statement comes from infinite descent. So if there's not an infinite number, if there's a finite number of numbers between 0 and a, then this above condition cannot be satisfied. Therefore, if a cannot equal 0, it must equal, if a cannot equal 0, the only integer it can equal is 0. And we could apply the same logic for b and c. So then we get to the conclusion that a equals b equals c equals 0. A bit of a tricky question to get our heads around, but this just used a bit of infinite descent and logic. The main takeaway from this question is that if we consider when a is 0 and where a is an integer, we have to consider what's between the integer a and 0, which is a finite number of terms, and we've got a condition that happens infinitely many times. We've got two opposing statements going on, therefore we can reject our initial assumption that a equals b equals c, a, b, c does not equal 0. A bit confusing, but we like this sort of stuff. So that's it for today's step question. Bit of a fun proof, but we done well. Alright guys, see you in the next video. Goodbye.